we begin with the first point is to have a look at the derivative of the natural log of x. Now there's a special reason for taking ln of x, log to base e, as you will see when we actually derive the derivative. And we use this result to then enable us to find the derivative of all other log functions, in fact, and quite easily. And I think you will see from this why the derivative, or rather the natural log of x, is rather important in mathematics, rather than say log to base 10 or something like that. So if we want to find what the derivative is and we have no idea, we have no other choice but go back to first principles. And if you recall, when we started finding the derivatives of various functions, the derivative is defined as a limit as this quantity h tends to 0 of a change in y, which is f of x plus h minus f of x over a change in x, which is the quantity h. That is the definition of the derivative, and we go right back to first principles to find it for the natural log of x. So the first step always is to substitute the value for the function. So this becomes the limit as h tends to 0. F of x plus h for our function becomes ln of no longer x but x plus h minus the function, which is ln of x all over h. And now before we can examine how that expression behaves as h tends to 0, we need to simplify it first of all, and even after that go through some changes in the function so it's easy to see what happens as the value of h tends towards 0. So using some properties of logs, I can simplify the expression somewhat. That's the limit as h tends to 0 of, we're subtracting, so I can in the numerator write this as ln of x plus h over x. Okay, all over h. And then perhaps an unnecessary step, but just to show you that we are applying another property of logs to simplify it further, I can write this over h as 1 over h times ln of x plus h over h. Because if you're multiplying by a number 1 over h, by your properties of logs, you can take this number to the power of 1 over h. Okay? So that is equal to the lim as h tends to 0 of the natural log x plus, well, let's not write it as x plus h, we can simplify that further. Just divide through by the x, and we will get 1 plus h over x raised to the power 1 over h. So we've simplified that in some way. But now, if you let h tends towards 0, you still don't get an unsatisfactory result because you're raising this to 1 over infinity. And in fact, with some slight manipulation to this expression, we can actually see what happens as h tends to 0, because a limit, in fact, does exist. So on the next board, I'll just put down the changes that I make, and I think in a few moments, once I do that, you'll see why I've made these changes. Rather than work with h over x, I'm going to define a new quantity. So I don't want to talk about h tending towards 0, but I'm talking about something tending towards infinity. And you'll see why. So I can define, say, a quantity, let's call it m, be equal to that expression, except I want it to be the other way around. Again, the reason for that will become apparent because I want to have 1 over m over here. So I write m as x over h. And don't think of x varying all the time. Although it is your variable, we are considering what happens as h tends towards 0. So for every specific value of x, what happens to that expression as h tends towards 0? So we could therefore examine all the possible values of x. So we're holding that fixed, as it were, while we examine the limit as h tends towards 0. Well, if we make that substitution, that change, then we will know that m tends towards what as h tends towards 0? M will tend towards a very large number, infinity, as h tends towards 0. So I can rewrite the expression I have here for this ln function in terms of m's rather than h's. So h over x is going to be equal to what? When I substitute, what is just that inverted? h over x is therefore 1 over m. And if you look at this expression, that gets h over x written in terms of m. I've got a 1 over h here, and I want to get rid of my h's, rather write them in terms of m. So what is 1 over h equal to? From this, I think you can see if we divide through by x, we'll get 1 over h equals m over x. So that's what it would be. And 1 over h is equal to m over x. Then I can make this substitution and consider what happens as m tends towards infinity. So you'll see why in a moment. So the derivative f dashed of x can now be written as the limit. Well, as h tends towards 0 is the same thing as saying now, as m tends towards infinity, of the natural log of 1 plus h over x, I said I can rewrite as 1 over m. Okay, and I raise that to the power 1 over h, which I can write as m over x. So I've rewritten the log function in terms of m's now, except for that variable x, which we say is fixed for the time being. And again, I can simplify that a little more, so hopefully you'll recognize what we're getting at. Let's say that's equal to the limit as m tends towards infinity, and I want to isolate my m's now. So I could rewrite this as ln 1 plus 1 over m to the power m, and then outside the square bracket, take it to the power 1 over x. Just one of the index rules. So I get my x 1 over x outside the square brackets. And now applying a property of logs, this is equal to the limit as m tends towards infinity. I'm raising a log to the power, so this could be written as, I beg your pardon, that square bracket, of course, is in the wrong place. It's ln of this function, so that bracket applies to that. And now, as I'm taking the ln of a number raised to 1 over x, it's the same as 1 over x times ln of that number. 1 over x ln of, did I write it in square brackets? Yeah. 1 plus 1 over m to the m. And some of you might recognize this expression 1 plus 1 over m to the m. We were dealing with it only a lecture or two ago. If you haven't recognized it yet, you should recognize its form in a moment if I just rearrange my limit now, because that 1 over x we're fixing for the time being while m tends towards infinity, so it come to the left of the limit sign. So this would be equal to 1 over x times the limit as m tends towards infinity of, let's get the ln in first, ln of square brackets 1 plus 1 over m in round brackets to the m. And again, one can rewrite that because we are taking the natural log of a number in here which is tending towards something possibly. So the limit really can apply to inside the log function. So that would be 1 over x times ln of, and the number is that we're going to use is as m tends towards infinity of 1 plus 1 over m to the m. And that is why I made the substitution on the right-hand board, because you can't actually see it from what I had on the left-hand side up here. Look at the square brackets, the way I've rearranged it. Now if we examine the limit of the expression inside the square brackets, do you recognize it at all? Not so sure. Some heads nod, some shake. When we were dealing with exponential functions about 2 lectures ago, we looked at a mathematical constant e, did we not? Something you've touched on in compound interest. What was the definition of e? That's exactly it. 1 plus 1 over m to the power m as m gets very, very large, in fact tends towards infinity. It came out to the value of e. This is why natural logs in mathematics are so useful, because this number keeps on coming up. So that will have a limit. This will be 1 over x times the natural log of the number e. And what is the natural log of e? It's log to base e of e, which is 1. So we have found from first principles the derivative of ln of x is 1 over x.